we're going to attach a mass of 11.2 kilograms onto a spring, and we're going to stretch the spring using 35 joules of work. And from this, we need to find our spring constant K if our spring stretches by 14.1 centimeters. Okay, so I already see something that is going to end up needing to be converted. This 14.1 centimeters is going to have to be converted to meters to be able to use them. So that would end up being 0.141 meters. I'm just going to do that conversion right now. So what's our max kinetic energy that this system could have? And what would be the speed at that point? Max kinetic energy this could have. Okay, so we know that work converts to potential energy, and they both have units of joules, so they'll convert directly. We can use our potential energy equation 1012, and let me show you what that one is. Potential energy times our spring constant. This is an equation that you'll be using. There's a test question that does require this, and you're going to want to be able to use this equation to solve for work done. Let's start to put some of these into this equation. So let me just write that out. So we've got a potential energy of 35 joules because of the direct conversion from work to potential energy. Just plug it in. We've got 1/2 times our constant, our spring constant. We don't know what that is yet. We're going to try to solve for that. Times 0.141 meters squared. Okay, so now we're going to need to solve for K. So we're going to isolate this K. So we've got our 35 joules over here, and let's multiply that times the 1/2. We're going to take the reciprocal of this 1/2. So that ends up being a 2 over here. And then we're going to divide it by this 0.141 meters, and this will keep the K by itself. Okay, so here we can convert our joules. I'm going to just save space. Go ahead and do that right now. So I'm erasing this joules, and I'll put it in red to show you that I'm converting it. But my joules will end up converting to Newton meter, or Newton times meter. And so what that then will allow us to do is we can cancel the meter from the top, and we can also cancel the exponent of 2. So we'll just end up with Newton divided by meter. And that's good because we're trying to solve for K, and that is the unit that we will need for our K. So if we were to plug all these numerical values into our calculator, we would end up with a number that looks like this: 3,520.95 Newton meters. Now, you're not going to see the Newton meter in your calculator, but we need to convert that to significant figures. So 2 significant figures because we are dividing by a 2 sig fig number. So that makes us need 2 sig figs. So that is going to look like this: 3.5 times 10 to the 3rd Newton meters. Now, we're not done yet. This is a multi-step problem. Okay, so we're talking about energy. We know that the max kinetic energy is going to be equal to the max potential energy because all of the energy will have converted. Well, let me just show you what that looks like if I was to graph out a waveform that represents this. Okay, so here, from here to here, we've got our amplitude. That's also, in this case, the same as delta x. Okay, and here we've got our max potential energy because you're at the peak before uh, you let go of the mass and it starts to bounce, right? So as soon as you let go of the mass, it's got all this tension on the spring. It's pulling it back towards equilibrium. And so you've got your max potential energy. You're going to hit your max point of acceleration as well. And then when we get to the equilibrium point, which would be right here across the middle, um, this is when the spring is back to its non-tensioned shape. But this is also the point after which you're going to have your max velocity. So we've got our max velocity right here, right as it crosses our equilibrium. That's also the point of our max kinetic energy, right there at that point where it crosses. Okay? Once we cross that equilibrium point, now we're pressing in on the spring is in compression. So here you've got the pulling motion, pulling it back towards equilibrium. As soon as it hits equilibrium, it starts to compress the spring, and then we have the spring providing a pushing force back the opposite direction. So that's what causes that oscillating motion. We know that our max kinetic energy is going to be the same as our max potential energy. We already know what that is, which is 35 joules. Mass kinetic energy means that all of our potential energy has converted. So we can use equation 1013. So we know our total energy is our kinetic energy plus our potential energy. And that is equal to 1/2 times our spring constant times our amplitude squared. Now, you may have seen this up here in the potential energy equation as the delta x squared, but we know that the amplitude is the same as the delta x. You can tell from this diagram over here. Okay, so that's our total energy. Well, we know our amplitude is the same as our delta x, which is the same as 0.141 meters. And that is our stretch, right, that we converted out to meters. So let's plug in our known values. We know that the total energy of the system is 35 joules because that was the energy introduced into the system earlier. So 35 joules when we stretched out the spring is equal to 1/2. Just plug it in into our equation here, this part right there. So 1/2 times our 3.5 times 10 to the third Newton meters. And I got that here. That's our K. Okay, so there's our K. So 1/2 times K times our amplitude squared, which is our delta x squared, 0.141 meters squared. Okay, and if you were to plug all this in, it would equal 35 joules. Okay, so that's our total energy. So we can use the kinetic energy equation that we learned in chapter 7. This is not a step you actually have to spend time working, but these should balance out if you were to plug them into the calculator. Okay, so we've got our kinetic energy equation from chapter 7. Your kinetic energy is equal to 1/2. So if we are at max kinetic energy, we know that all the potential energy has been converted. So what did we start with? It was all potential energy, which was the total energy in our system. So that 35 joules of potential energy has to all transfer to kinetic energy. This would be like a perfect solution with nothing lost. So our kinetic energy should, at its max, be 35 joules. Okay, and then we keep everything 1/2 mv squared. We already know what the mass is. It's up here, 11.2 kilograms. So we can go ahead and plug that in here. So 1/2 times 11.2 kilograms. So 11.2 kilograms times our v squared, which we don't know what that is yet. We're trying to solve for that. So we have to divide all of this off. We're going to bring it over here to this side and isolate the v squared by itself. And so we got 35 joules divided by 5.6 kilograms. These are all the intermediate steps. It's equal to v squared. So that ends up being 6.25. Okay, but we're going to have to take the square root of that because we got to get rid of that v squared and get it just to be v by itself. So I'm highlighting that in red. Okay, and then of course we got our meters per second squared. Ooh, let me write that in here really fast. Meters squared per second squared. Okay, that's going to end up just becoming meters per second because we're looking for just a simple velocity here. So if I was to punch everything into the calculator, I would end up with 2.5 meters per second is equal to my velocity after I take the square root of everything. This is meters squared per second squared here. So this is the velocity, and that would serve for the speed at that point. So we found everything that was asked for. We found the max kinetic energy. We knew it was 35 joules. From there, we were able to use that to find our velocity.